Welcome to this explainer. Today we're going to take what looks like just a daunting wall of letters and numbers and completely transform it into a master key. Seriously, the periodic table isn't just some boring chart you had to memorize in high school. It's the ultimate cheat sheet. It literally unlocks how absolutely all matter in the universe behaves. So let's just dive right in, because once you know how to read it, the whole world kind of makes a lot more sense.
What's really fascinating here is that the human desire to understand matter, it didn't start in some sterile modern lab. No way. For thousands of years, alchemy was actually the primary focus for early scientists. And they had these two incredibly ambitious goals, right? They wanted to find a cure-all for diseases, to grant eternal life, and they desperately wanted to turn common, everyday metals into gold. They genuinely believed that all matter was just different combinations of basic elements, and they figured, hey, if we can just crack the ratio, we can make literally anything. Now, okay, obviously they never found the secret to eternal life or unlimited gold, but their centuries-long quest for order absolutely sparked the methods and techniques that would eventually birth modern chemistry.
So here's our map for today. We're going to cover the quest for order, cracking the atomic code, decoding rows and columns, the shielding effect, and finally, predicting element behavior.
All right, let's kick things off with Section 1, the quest for order.
Our journey actually begins back in the 19th century, which was basically an era of elemental chaos. Chemists had discovered dozens of elements by then, but they were just desperately searching for some kind of system to organize them all. Fast-tracking through history a bit, we can see how this giant puzzle was pieced together. Back in the 1820s, a German chemist named Dobereiner noticed these things called triads, groups of 3 elements where the middle one happened to have the exact average atomic mass of the other 2. Pretty cool, but it really only worked for a few elements. Fast forward to 1864, and a British chemist named Newlands proposed the law of octaves. He noticed the chemical properties repeated every 8th element, kind of like musical notes. But again, still incomplete. There was simply no room for undiscovered elements. Finally, the Russian chemist Mendeleev made a massive, game-changing leap. He arranged the known elements in horizontal rows by increasing atomic mass. But the genius part? He left blank gaps, actually predicting the properties of elements that hadn't even been discovered yet. It was absolutely revolutionary, but, well, it still wasn't quite perfect.
Which brings us to Section 2, cracking the atomic code.
See, while Mendeleev's table was total genius, organizing by atomic mass couldn't perfectly explain the placement of certain elements or isotopes. We needed a deeper truth to tie it all together. And that monumental breakthrough, the one that gave us the modern predictive map we use today, happened in 1913. H. Moseley discovered a brand new property, the atomic number. Now, this is simply the exact number of electrons in a neutral atom. Moseley realized that the atomic number, and not atomic mass, is the true fundamental property that dictates an element's behavior. Why? Because it increases by exactly 1 from element to element, and absolutely no 2 elements can ever share the same number. It's like a unique fingerprint. Because of this, Moseley amended Mendeleev's original periodic law. And that's why our modern table is built on this foundation. The properties of elements are a periodic function of their atomic numbers.
Moving right along to Section 3, decoding rows and columns.
So to properly read this newly decoded map, it really is all about electronic configuration. Just as a quick refresher, as you read horizontally across the periods, so from left to right, the atomic number continuously increases. That means the electronic configuration changes continuously too. And as a result, the properties of the elements smoothly shift along the way. But the vertical columns, the groups, well, they're a different story entirely. Elements in a vertical group don't have continuously increasing atomic numbers. There are these irregular gaps between them. But here is the kicker. They share the exact same number of electrons in their outermost valence shell. Because of this really elegant design feature, elements in the same group act like a family. They demonstrate highly similar, super predictable chemical properties.
To make things even easier, the map is further divided into specific neighborhoods called blocks. Depending on the type of subshell that is actively receiving the element's final, outermost electron, we categorize elements into S, P, D, and F blocks. For example, groups 1 and 2, those highly reactive alkali metals, they're busy filling their S subshell. Over on the far right, groups 13 to 18 are filling their P subshell. The D block, that covers all the transition metals right there in the middle. And finally, the F block houses those 2 separate long series floating at the very bottom, the lanthanides and actinides.
All right, let's jump into Section 4, the shielding effect.
Everything we've talked about builds into a vital, mechanical concept that acts as the hidden engine behind the entire table's behavior. We call it the shielding effect. Okay, I want you to imagine the nucleus of an atom as a super powerful magnet desperately trying to pull all of its electrons closely toward it. But as atoms get larger, they add more and more inner shells of electrons. These inner electrons literally get in the way. They physically block or shield the nucleus's attractive pull on those outermost or valence electrons. Because of this screening effect, the outermost electrons feel a much weaker pull than the actual positive charge of the nucleus.
To put that into perspective, let's consider sodium and potassium, both from the very first group. Sodium has fewer electron shells, so its outer electron is held pretty tightly. But potassium, sitting right below it on the periodic table, has a whole extra shell. Those inner rings act like a thick physical shield. Because its outer electron is far more shielded from that positive nucleus, it's barely holding on. That makes it incredibly easy to just pull right away. This totally explains why the shielding effect steadily increases as you move down any given group.
Which leads us perfectly into Section 5, Predicting Element Behavior.
Armed with an understanding of this hidden engine, we can now predict exactly how elements are going to behave and interact in the real world. First up, let's talk about the actual physical size of atoms, their atomic radii. Now, because you're adding entire new shells of electrons, which, as we know, increases the shielding effect, atomic sizes predictably grow massive as you move from top to bottom down a vertical group. But watch what happens as you travel horizontally across the period from left to right. Even though you are adding more electrons and increasing the atomic number, the atoms actually shrink. I know, it sounds counterintuitive, but it's because no new shells are being added to shield the electrons, while the nucleus is constantly gaining more positive charge, such as pulling that outer shell tighter and tighter toward the center.
Because we know exactly how tightly the nucleus is pulling, this map flawlessly predicts three major chemical traits. First is ionization energy, basically how much energy it takes to just rip an electron away. Second is electron affinity, the energy released when an atom eagerly accepts a brand new electron. And third is electronegativity, an atom's power to hog shared electrons in a chemical bond. And here is the beautiful symmetry of the whole thing. All three of these traits follow an identical, totally predictable trend. Because atoms get smaller and tighter from left to right, all three of these values universally increase across the period. And because atoms get bigger and more shielded from top to bottom, all three values decrease as you go down a group. It's almost unbelievably perfectly ordered.
Now, I really want to make sure you know, this isn't just some abstract theory meant for a chemistry exam. This has spectacular, real-world applications. Just think about the explosive, brilliant displays of fireworks. The colors bursting in the sky are entirely predictable based on these exact chemical properties of different metal salts. The specific electron configurations mean that when heated, sodium is always going to burn a bright yellow. Calcium gives you red, strontium burns scarlet, barium flashes a brilliant green, and copper provides this really beautiful bluish green. Skilled professionals are literally using this exact periodic predictability to paint the night sky. How cool is that?
So the periodic table we have today is honestly a triumph of human intellect. From the early alchemists endlessly searching for gold, all the way to modern physicists smashing atoms together, we have completely uncovered the systematic rhythm of the universe. But, the map isn't totally finished yet. Down at the very bottom of the table in the 7th period, scientists are briefly creating these highly unstable, super heavy synthetic elements in laboratories. And as we continue to fill in this map, it leaves us with an incredibly thrilling mystery. As we push further and further into the unknown, what undiscovered explosive behaviors are just waiting for us at the very edges of the periodic table? Keep that in mind the next time you look at this incredible chart. Thank you so much for joining me on this explainer, and keep learning.